So why was 1 mole of oxygen excited when he walked out of the singles bar? Because he got Avogadro's number. Come on, that was a good one there. Intro to gas stoichiometry and the use of the ideal gas law, PV equals nRT, when the reaction is not at STP. Remember that at STP, 1 mole of a gas equals 1 mole, and I'll put G for gas, equals 22.4 liters. Well, what happens when we're not at STP? We know that changes in pressure and temperature can affect the volume of gases. So using our gas stoichiometry, and when we have problems that involve a chemical reaction, you know it's going to be stoichiometry. You need to apply the stoichiometry to the reaction, and then when you're given different temperatures and pressures, as you can see down here, you need to use the ideal gas law to solve for it. So let's do an example problem, and it'll make sense because it's using all of the information that you know already. What volume of a gas, so this is volume, will be given off when 10 grams of calcium carbonate is decomposed? So up here, I'm going to put down my 10 grams of calcium carbonate, and it wants to know what volume of a gas. So volume is unknown because this is my gas. The temperature that this occurs at is 50 degrees Celsius, so that's my temperature, and a pressure of 754 millimeters of mercury. Well, if I remember my GMA, right, grams, moles, and instead of atoms, we can do volume, GMV, and then the same thing here, I have a GMV, and remember, we have a mole ratio and we have a volume ratio that we can use now. I can go from grams to moles, and then to get from moles to volume, you have to use the 1 mole is 22.4 liters. Well, that's at STP. This reaction is not happening at STP, so I basically have eliminated this side of my map for myself. So what I have to do instead here is get from grams to moles and then moles to moles, right? So I need to get to moles of this, because remember, moles is N. So if I can find N of CO2, then I can plug in this up here, my temperature and pressure, there's temperature, there's pressure, and I can solve for the volume, which is your unknown, at those new conditions. So let's go ahead and do that. So I'm going to mole ratio, or I'm going to get grams to moles of CaCO3, and then I'm going to mole ratio CaCO3 to CO2. So let's start here with my 10 grams of CaCO3. I'm going to get grams to moles. So 1 mole of CaCO3 to grams of CaCO3. I need to add up off my periodic table a calcium, a carbon, and 3 oxygens. So let's go ahead and do that. Adding all those up, we get 100.09 grams. So my grams cancel. I'm now in moles of CaCO3, so I'm going to bring down moles of CaCO3, and I'm going to, from a mole to mole, I'm going to moles of CO2. So what is my mole ratio here? 1 to 1. That's a nice, easy, convenient mole ratio. And now I simply just take my 10 divided by the 100.09, and we end up with 0.099 moles of CO2. So this is your N value. Remember, moles is N. So I now know moles, which is up here, and I'm given this temperature and this pressure. So R is a constant. I can now solve for the volume of this amount of moles of CO2. So let's go ahead and do that here. I'm going to, again, identify my variables here. Pressure is given at 754 millimeters of mercury. Remember, all of my pressure units have to be in atmospheres. So I'm going to convert millimeters of mercury to atmospheres. If you forget how to do that, you need to grab your equation card that you should have. And I have my pressure conversion, 760 millimeters of mercury equals 1 atmosphere. So 760 to 1 atmosphere is going to be 0.992 ATM, atmospheres. There's my pressure. My volume is unknown. Remember, that's what we're trying to solve for up here. My temperature is right here. It's 50 degrees Celsius. So I need to add 273 to that. So real quick here, get 323 Kelvin. So there's PV. N is right here, so there's my N, and R is a constant, 0.0821. So let's go ahead and substitute these in for my problem. So P is going to be my 0.99, so 0.992 atmospheres. V is unknown, so I'm going to leave that as V, equals nRT, N, 0.0999 moles. R is 0.0821, and T is the 323. So 0.099 moles at this pressure and temperature will give me what volume? Now it's a very easy solve here when I'm going to divide each side by the 0.992 on each side. 0.992, and now I just need to type in my calculator the numerator divided by the denominator. Typing that in my calculator, we end up with 2.67 liters of my CO2 gas produced, and that's using gas stoichiometry and then the ideal gas law to solve for one of these problems. Let's go ahead and take another look at another example problem for using this type of problem-solving technique. Here's our second gas stoichiometry problem when we're dealing with items that are not at STP. So suppose we're going to go up Mount Everest, and the temperature's up there, negative 27 degrees. That's a bit cold in the summertime, and the pressures are right around 30 kPa. That's a low pressure. Remember, 101.3 kPa is what it is on Earth's surface. So the higher you go up, the lower pressure there is because there's less gas sitting on top of you. So to help us stay warm and cook some food, we're going to take some propane to burn. Our propane tank has 2 liters of propane gas. So down here, this is propane. I'm just going to label that as 2 liters. How many liters, so that's volume, unknown, of oxygen will need to be reacted to burn all the propane? Well, since I am at negative 27 degrees and 30 kPa, that's a different temperature and a different pressure than STP. So I can't just do liters to liters at STP because the gas is going to have a different volume when it's not at STP. So I need to find moles. So remember, N is moles. I need to do liters to moles, and then I'm going to substitute in my moles into PV equals nRT to solve for that volume. So it's kind of a multi-step problem that I'm going to be doing here. So we'll do the first one here where I'm going to use my stoichiometry to get liters of propane to moles of oxygen. And I'm just using our map, GM. What I'm going to do here is use my GM GMV, again, GMV, to solve my problem. Now, I'm currently starting 2 liters of propane gas, so I'm here. The reason I can't jump straight down to volume of my unknown is because this gas here is not at STP, while this gas here is held within my oxygen tank, so it's at a constant pressure and temperature, and it's a fixed volume of gas because it's inside of a propane tank. So the tank is basically sealed conditions. That I know that I can go from volume to moles and then moles to moles, but I just can't go right here because then moles of my oxygen gas, they're going to have a different volume based on the outside conditions. So I hope that makes some sense there and why we're doing this way, but that's what we need to do. So I'm setting up here 2 liters of my propane C3H8, and I need to convert that to moles of propane, where remember 22.4 liters is equal to 1 mole of my propane, C3H8. Liters cancel. I'm now in moles. I can do a mole to mole ratio, which is a 5 oxygen to 1 C3H8. So 1 mole of C3H8 to 5 moles of oxygen. And simply divide here and then multiply by 5 to get our answer. We get an answer of 0.446 moles of oxygen. So that's my N, that's my moles of oxygen. I can now use the ideal gas law because I'm at these temperature settings, this pressure and this temperature, to basically determine the volume of gas that is going to be consumed. So I'm going to go ahead and now use PV equals nRT to solve for the new volume of my oxygen gas. So my pressure is 30 kPa. So I'll kind of list these out over here. Pressure is 30 kPa, which we know we need those in atmospheres. So I'm going to convert it to atmospheres. So there's 101.3 kPa in 1 atmosphere. So doing the math, we can solve that one. My temperature is negative 27 degrees Celsius plus 273 to get it to Kelvin. My volume is the unknown variable. My R is a constant, which is 0.0821. And N, we just found, which is right here, the 0.446 moles. So real quick, let's solve this and pressure and temperature for our variables. Now, solving for pressure and temperature, we get 290 or 0.296 atmospheres, ATM, and then 300 Kelvin. So let's go ahead and substitute these in for the PV equals nRT. Pressure is going to be the 0.296 ATM. V is unknown, so I'm going to leave that as V, equals N 0.446 moles. R is 0.0821, and T is 300 Kelvin. Very simple to solve here now. I can just divide each side by 0.296. That gets rid of this. Over on this side, I want to do the same. Divide by 0.296. And my volume, as we solve, is 37.1 liters of oxygen gas will be consumed at that pressure and temperature. And that's how you use the ideal gas law to solve with stoichiometry problems that are not at STP.